Okay, so last time we determined whether the MLE for the expectation of X was asymptotically unbiased for the expectation, and we said that it is because the expectation of mu hat, our estimator for the expectation, is one half n over n plus 1 times theta. And so the limit as n approaches infinity of this expectation is going to be theta over 2, because n over n plus 1 approaches 1 as n approaches infinity, and theta over 2 is the expectation of x, so that is satisfied. Do you have any questions about this?
No.
Okay. So my next question is our estimator mu hat unbiased? What do you think about that?
Yes. Because we prove it.
Why do you say that?
Yes, it's unbiased because we just improve it here.
We did not. What we were talking about in this last one is asymptotic unbiasedness.
Oh, okay, it's different.
And these are different.
Oh, okay.
Yes. This is important to remember, is that asymptotic unbiasedness does not imply unbiasedness. However, unbiasedness does imply asymptotic unbiasedness. And yeah, the reason we have a concept of asymptotic unbiasedness is that it is useful in situations where we have an estimator that may be biased, but for large values of n, the bias is negligible because it approaches the true value of the parameter. The expectation approaches the true value of the parameter. Now, looking at mu hat, would we say that mu hat is unbiased? What would you say about that?
Yes, because it's equal to mu.
No, our estimator mu hat is based on the sample. So remember that mu hat here, which is the MLE for mu, which we are just defining as the expectation of x, is equal to the sample maximum xn divided by 2. And what we want to know is this unbiased? And so what do we need to look at in order to answer this question?
The xn.
We need to look at the expectation of mu hat.
Okay.
Because what is the definition of unbiasedness again?
So probably it's the point. It's not straight. The point is it's not symmetric, probably.
No, so unbiasedness is talking about the expectation of a random variable. And our definition for this, which this is extremely important to remember, is that an estimator theta hat is unbiased for theta, or in other words, is an unbiased estimator for theta, if and only if the expectation of theta hat equals theta. And similarly, we're talking about asymptotic unbiasedness, so I might as well put that here as well.
Okay.
An estimator theta hat is asymptotically unbiased. For theta, if and only if the limit as n approaches infinity of the expectation of theta hat is equal to theta. Does this make sense? How these things are different?
Yes.
Okay. So then, in determining whether mu hat is unbiased, we need to look at its expectation. So the expectation of mu hat, we actually talked about this the last time we were looking at these problems. And we said that because the expectation of x, parentheses n, sample maximum, is n over n plus 1 times theta, that the expectation of mu hat is, I'm going to write this as n over n plus 1 times theta over 2. And so this is our expectation. And what is the important thing to note about this?
I think n over n plus 1 is sigma, I think, or...
So, all we need to know is that this is not equal to theta over 2, which is mu. So, this is our estimator for mu. But the expectation of our estimator is not equal to the parameter itself, mu. And so we would say that this is not biased. Or in other words, it is biased. First of all, does this make sense why this is a biased estimator?
So because it's equal to mu?
Because it's not equal to mu.
Because it's not equal to mu. Yeah, okay. So if it's equal to mu, then it's unbiased.
If the expectation is equal to mu, then it is unbiased.
Okay.
And so now the second part of this question is how can we use this to get an unbiased estimator? For mu. What can we do with this? Do you have thoughts on how we can use the MLE to get an unbiased estimator?
How is that?
So, I'll say that we will propose an unbiased estimator which I will call mu tilde. And we'll say that this is equal to A times mu hat for some value A. So I'm saying that we may be able to get an unbiased estimator by multiplying our biased estimator by some scaling factor. Does this make sense?
Yes.
Okay. And so then, let's look at the expectation of mu tilde. This is equal to the expectation of A times mu hat, so that's just substituting in what we defined for mu tilde. And then how do we write this one?
Okay, we take
What's our next step in?
the A out, right?
Take the A out. So this is A expectation of mu hat. And what is the expectation of mu hat again?
Expectation of mu hat. Mu.
No, the whole purpose of this is that the expectation of mu hat is not mu. Because if it was, then we would already have an unbiased estimator.
Okay.
So look at what we've written before. What is the expectation of mu hat?
Yeah, the n over n plus 1 by theta. Oh, that one.
Yeah. And theta over 2 is equal to mu. So I'll write this as A times n over n plus 1 times mu. And now where do we go from here?
Take not sure.
Okay, so what we'll do here is we will set this equal to mu and solve for A. Because we want to get a value of A such that this expectation here is equal to mu. And so if I say that this is equal to mu, then A is equal to mu over n over n plus 1 times mu. And so this is equal to n plus 1 over n. Does this make sense?
Let me see. Okay.
Okay, and so then what is our estimator mu tilde?
No, I'm sorry. So how like why? So you put mu for both in here in what is that called? Because I see you put two mu there.
So I took the expectation of mu tilde, which is this whole thing, and I set this equal to mu because I want to find the value of A that makes this equal to mu. Does that make sense so far?
You don't do multiplication. You don't multiply. No, you just.
I divide by the n over n plus 1 times mu.
How? You divide the whole thing? Like, can you explain more?
Because I'm trying to solve for A.
Okay, so you try to
this is just algebra. So we have A equals this term here, or sorry, A times this term here equals mu. So A equals mu divided by the term in orange. It's just a matter of dividing this over to this side of the equation,
okay,
so that we get A by itself.
Yeah, now I understand.
Okay. So this mu tilde, which we said is A times mu hat, and so if this is A, here the n plus 1 over n, and mu hat is beta over 2, what can we say about this?
It's unbiased.
It's unbiased for beta, or for NB. Does that make sense?
Yes.
Okay. And so this is all for the second problem. Do you have any questions about this?
I think we already made that. We did the second problem, right? So
I mean, problem 2, parts like ABC. So this finishes out example 2. Do you have questions about any of this?
oh, okay. Because I thought you was doing the problem 3. So you answered problem 2, but now you just explaining it, right? You just make explanation for problem 2.
We didn't do part C until just now.
Oh, so we did not do C.
Yes, we did not do C last time.
Okay, all right, okay. That makes sense.
Okay. So going on to example 3. Here we say that X follows a beta distribution with parameters 1 and beta. And first, we want to find the maximum. Go ahead.
Yes, because I see in the notes that there's you already did the question 2, number 3. That when we put the variance x equal expectation square minus the expectations, when you put the variance there, then you put the integration. Because I wrote this answer on my notebook, and
we didn't do this problem.
No, for number 2, because I was talking about like yesterday, because I wrote this in my notebook. Question 2 for number 3, C, I think. Yes.
So this is from your
for C, because you talked about it yesterday, and you stated that this variance var x equal expectation square. I think you wrote this already.
No, we didn't.
Probably
that was with a different distribution. That was with an exponential distribution.
If you scroll down, or I'm not sure.
The distribution is different. One's a beta distribution, one's an exponential distribution.
Okay, so this is from your example, right?
Yes, this is my example.
Oh, okay. I thought that this was the homework. Sorry.
Oh, is that what you wanted to talk about?
No. I was thinking, because like, did you remember the third problem that we left? We did not talk about. You did complete it. You complete some, but then you left it. But it's fine. You can keep going. You can continue.
Okay. So example 3 here. We suppose that X follows a beta distribution, parameters 1 and beta, And so here we're saying that the alpha is known. And in fact, this having it specifically be 1 simplifies the problem. And for part A, we're asked to find the maximum likelihood estimator of the variance of x. So what is our first step to this?
You don't put product. I'm not sure if you...
Okay. So first step is to find the likelihood function. And it's always a good idea with these to just start by writing out the density function. And here, what I mean by this is shorthand that x1 up through xn are IID beta 1 beta. So it's a random sample from this distribution. So our density function for beta, or for x rather, is equal to gamma of alpha plus beta over gamma of alpha times gamma of beta times x to the alpha minus 1 times 1 minus x to the beta minus 1. And so inserting what we know about this, we can say that this is gamma of alpha plus beta over gamma of alpha, or sorry, I should be substituting 1 in place of alpha. So this is 1 plus beta. This is gamma of 1, gamma of beta, x to the, I plug in 1 for alpha. This is x to the 1 minus 1 times 1 minus x to the beta minus 1. And now, what properties can we apply to simplify this further? So we have a property of the gamma function. We have 2 properties that are important here. One is that gamma of n is equal to n minus 1 factorial for integer values, or rather positive integer values of n. And the other property we use is that gamma of z plus 1 is equal to z times gamma of z for any z. In fact, any z and the complex numbers. So that's a very broad formula. But these are the two things that we apply here. And what does that give us?
We just have the gamma 1, gamma beta. We just we'll fix this, or I'm not sure.
Okay, so let's start with the numerator here. Gamma of 1 plus beta. What property can we apply to simplify that numerator?
Does beta gamma beta, or 1 gamma?
This will be beta gamma of beta. Okay?
Okay.
What is gamma of 1?
Just 1 factorial, probably.
It's 0 factorial. And so what does that evaluate to?
Okay, 0 factorial. Okay.
And what is 0 factorial?
0 or 1?
It's 0.
Okay.
Yeah. That's just how it's defined. So that's 1. And then what is gamma of beta? Actually, we don't need to evaluate gamma of beta, because we'll write gamma of beta here. And now these things will cancel. And this whole thing is just going to be beta. X to the 1 minus 1 is 1. So we have 1 minus x to the beta minus 1. And we're left with beta times 1 minus x to the beta minus 1. Do you have any questions about this?
No.
Okay. So, again, this is not the likelihood function yet. This is the density for a single x. And so now our likelihood function. How do we get our likelihood function?
I'm not sure.
Okay, so we know that our xi's are independent. And anytime we have a sample of independent observations, we can use the same technique for finding the likelihood function. And so what do we get as the result of that? Or else, what formula do we apply?
Let's see.
We're going to take the product.
Probably we need to choose formula from the sheet or something.
No, we're going to take the product.
Okay.
of all of these individual densities. So this is the product from I equals 1 to n of beta times 1 minus x to the power of beta minus 1. And then what do we get?
Can we take the beta minus 1, take it down, or take it beside the product, something?
We can't take it down. Let's start with the beta out front. What can we do about the beta out front?
Okay.
What can we do about that?
Just put it beside the product. Transfer it. No?
Take it outside the product, and when we do that, it will turn into beta to the n, and then the product from I equals 1 to n of 1 minus x to the beta minus 1. And there's not really much worthwhile, there's not really anything worthwhile to do after that in terms of simplifying the likelihood function itself. But if our goal is to maximize this function, what is our next step going to be?
Integration.
No, so we want to differentiate later. We'll need to do the second derivative test to try and find a maximum for this distribution. For the likelihood function. But before we differentiate, what do we want to do? Since differentiating right now would be really intractable because we have that good product there. So what can we do instead of differentiating directly?
Not sure.
We take the logarithm. Anytime you see a likelihood function that you are hoping to differentiate, your first thought should be that you should take the logarithm of it.
Okay.
And so our log likelihood function, lowercase l of beta given x, what is this going to evaluate to? If it's the log of this whole thing up here, how can I start simplifying that?
We put log for beta and log for 1 minus x. We just put log there, 2 logs.
Okay, so we can split these up into log
beta
to the n plus log of the product I equals 1 to n of 1 minus x beta minus 1 to the beta minus 1.
Okay. I have a question. So because this is the first time I see, like when we took beta in front of the product, we put n there, like But we did not did this before. I'm not sure why. Like we put n in the power of the beta when we transfer it, when we move it.
What do you mean we didn't do this before?
Yeah, I mean, this is the first time I noticed this. Like when you take beta out, you put the n, and we do the power n.
No, we did this every time. Something analogous to this.
Probably
So
I forget, or I'm not sure.
here we had beta to the n for that one, and then for the first one we weren't doing likelihood functions. Exponential distribution from problem 2 in the homework, we were looking at 1 over beta to the n, which we then wrote as beta to the negative n.
Okay, so it's always it should be there n. Is it possible if you can put numbers instead of n?
No, I need to put n.
Only n. Okay.
Because there's n is the sample size. You can't put anything in place of the sample size.
Okay.
I mean, if you know the sample size, you can put the sample size, but when we're solving this sort of problem, we typically don't have a particular sample size we're working with. We just have that n represents the sample size.
Okay.
Does that make sense?
Yes.
Okay. So now how do we simplify from here?
Okay, we have no, maybe n log beta, then plus log beta minus 1 multiplied by 1 minus x.
Okay, n log beta plus, and then how does the product split up?
Beta minus 1 multiplied by 1 minus x.
Okay, yeah, so we can, and these should be xi's here, sorry. We can bring beta minus 1 to the front, okay. And then what else can we do to it?
Then we have 1 minus x.
Okay, so if we have the log of the product from I equals 1 to n of 1 minus x, how do we split this up further?
Can we do log 1 and log minus x?
No.
Oh.
If you have addition inside of a logarithm, you can't split that up. But we have a product inside of the logarithm. So we can split this one up as our logarithm of the product turns into a sum from I equals 1 to n of log 1 minus xi. Does that make sense?
Oh, okay, yes.
Okay. So our next step with this is to do what?
We need to get rid of the log.
Not get rid of the log. We can't get rid of the log.
We can do exponential.
And this is as much as this is no. This is as much as we can simplify the log likelihood.
Okay.
So what's our next step?
I'm not sure.
So remember that we're trying to maximize the log likelihood function.
Yes, so you do the derivative, right?
Derivative, yes, with respect to beta. Okay, so starting with this term here, what is the derivative of that?
Minus 1. Maybe 2n over, like, probably add 1, it become 2. Then we have power of minus 1. Forget.
Okay, so as a reminder, the derivative, and we're taking the derivative with respect to beta, but the derivative with respect to x of log of u, where u is some function of x, is equal to u prime over u, where u prime is the derivative of u with respect to x. So that's what we're applying here again. Or we can just say that the derivative, the simplified version, is that the derivative of x, sorry, the derivative with respect to x as log of x is 1 over x. And so then, for this one right here, what do we get as the derivative of n log beta?
Derivative n log beta. Okay, we have beta or beta over
So this is going to be n over beta.
Okay.
That's all that first term is. Does that make sense?
n over beta. Okay. Okay, makes sense.
And then what is the derivative of the second part?
Let's be so it's derivative with respect to beta or with x.
Derivative with respect to beta of that whole second term. So derivative of this thing with respect to beta is just 1. And so then all we've got left is our coefficient here, which is this whole thing. So this is going to be past the sum from I equals 1 to n of log 1 minus xi. Does that make sense?
Yes. Because since we take derivative of beta, so we just focus on the beta and we ignore the rest, right?
I wouldn't say we ignore the rest, but we treat the rest of it as constant.
Okay. All right.
And so what is our next step?
So we take the first derivative, right? So now we have to do the second derivative.
Okay, we can do that now if you'd like. So then what is the second derivative of this?
Minus 1 over... not sure what's the derivative for n over beta.
So we can write this if we want as n times beta to the negative first. Does that make sense?
Okay. Yes.
And so now, what is the derivative of this thing in cyan with respect to beta?
Respect. So we don't with theta. I'm not sure. Okay. Yeah. So it's gonna be -2. Like we increase the power. So it's -2 n beta 0. Then it become 1, like -2n.
No, we reduce the power. So this turns into negative n over beta squared. Because the power goes from -1 to -2.
Okay.
And now, what is the second term? Differentiated with respect to beta.
Differentiate with respect to theta. What's the second term? Just leave it constant. Leave it.
Yeah, so we treat it as a constant, and so its derivative with respect to beta is 0.
Okay.
Does that make sense?
Yes.
Okay. And then what do we do with the first derivative?
But why we don't put a 0 from the first derivative? So from the first derivative we could put a 0, right?
Mm-hmm. Yeah. You suggested going to the second derivative, though. So yeah, we'd like to set this equal to 0. And when we do that, these things are replaced with beta hats. Because now I'm talking about an estimator if I force this thing to be 0. And so then, setting this equal to 0, what do I do with it?
No, I said that you say the constant that we take it as 0 in the second derivative, right? this constant, the log.
Yes.
Uh, would, can we just put it 0 from the first derivative? Is it okay if it's gonna, the first derivative is just the n over beta hat and that's it? We ignore we put 0 in the constant, we just remove the whole thing, the expression, the log?
No.
Why?
Because this is the coefficient of beta here. This thing that I just underlined is getting multiplied by beta. So you differentiate the second term with respect to 0, or with respect to beta. The derivative is the sum of the log 1 minus xi.
Okay,
That's constant with respect to beta. It's not 0 though.
Okay, because so you put beta as 1, then become 0, then okay. Right? So beta become 1.
Beta become 1.
All right.
What do you mean by that? No. So the reason that this thing is not 0. This is a positive number. Actually, it's a negative number, but it's not 0.
Yeah, I was talking about
its derivative with respect to beta, though, is 0.
Okay. So when you take the first derivative, you just put the beta 0, and you leave everything else.
No, we're not setting beta equal to 0. So let me expand this.
Okay.
That might make it more clear what's going on. This is n log beta plus, we can expand this as beta sum from I equals 1 to n of log 1 minus xi minus 1 times the sum from I equals 1 to n log of 1 minus xi. So we differentiate that first term with respect to beta. We get n over beta, like we discussed. We differentiate the second term with respect to beta. This is just a linear term of beta, so its derivative is the coefficient here. We're multiplying beta by sum of log 1 minus xi. And so when we differentiate that, sum of log 1 minus xi is the derivative with respect to beta.
Okay.
Because what we're doing here is we're taking the derivative, so this is dd beta of a times beta, where here a is, and actually I'll just write this as the first derivative with respect to beta. And as long as a is not dependent on beta, this is equal to a. That's all we're doing here.
Okay. Makes sense.
So now that we've got both of the derivatives, our next step is to figure out where the first derivative is equal to 0. And so I set this thing equal to 0. And when I did that, I replaced the betas with beta hat. Because if we force this thing to be 0, we're not looking at the true value of beta anymore. We're looking at our estimate for beta. And now it's just a matter of solving for beta hat. And so what would I say that beta hat is then?
So beta hat is just equal to minus n over beta square, probably.
No, that's the second derivative of the log likelihood. What I'm asking, so set the second derivative aside for now, because we're gonna come back to that. But right now we're just focused on finding what value of beta hat makes the first derivative equal to 0.
What values make the first derivative equal? I'm not sure.
Okay. So we set this expression equal to 0, and now we just need to solve for beta hat. And our first step, we can look at just subtract this thing from both sides. So we got n over beta hat is equal to negative sum from I equals 1 to n of log 1 minus xi. And then beta hat we get by just cross multiplying and dividing these things. So we can switch the positions of those, and beta hat is equal to n divided by negative sum I equals 1 to n of log 1 minus xi. Now it may seem a little bit weird that here, if beta has to be a positive value, that we would have a result that has a negative in it. But remember that since x is between 0 and 1, 1 minus x. Excuse me, 1 minus x also is between 0 and 1. So the log of 1 minus x is a negative number. And so we're adding up a bunch of negative numbers, multiplying by negative 1, and now this is positive. And so beta hat is going to be positive. Does this make sense?
Okay. All right. So this is the final answer?
Well, we haven't checked the second derivative yet. All we need to know for the second derivative is that it's less than 0. And here, so that then we have a maximum. Here we've got n, which is positive, divided by beta squared, that has to be positive. We're multiplying by negative, so this is less than 0. So beta hat is the MLE. And I should say beta hat. So beta hat, this thing here, is the MLE for beta. Does that make sense?
Yes.
Okay. So we're a bit past the hour now. Do you want to stop here?
Yes.
Okay. So I will put, actually, I'll just export this to PDF now, and the link in the Google Doc updates automatically.
Okay.
And I'll put the Zoom recording in the Google Doc as well.
All right. Thank you, Ari. I will contact you. I will see when the next hour, because I have exam next Wednesday. So I will let you know by chat when is our next meeting. Okay. Thank you. Take care.
Okay. Oh, and I should mention that I'll have quite limited availability from Saturday to Tuesday. But I'll be available tomorrow and Friday. I'll have plenty of availability. And then yeah, I might be available Sunday, Monday, Tuesday. I'm not sure.
Okay, I will see. I will chat, and we will chat. I will see. Thank you.
Thank you.
Thank you.
Bye-bye.